Hi there. My name is Valery Kravchuk and I'm a principal support engineer in MariaDB Corporation. Today, even tonight, I'm going to present you a talk about dynamic tracing on Linux, in this case applied to MariaDB server, mostly 10.5 and 10.3 in some examples. I present this from a small town of Vyshgorod, located near the capital of Ukraine, Kyiv. I work in support of MySQL and related products for more than 15 years already. Of them last 4.5 years in MariaDB Corporation. Since I quit Oracle in 2012, I'm also a community member, a public person who writes about MySQL and MariaDB and speaks at various conferences. I write about MySQL and MariaDB in my blog, on Twitter, even on Facebook. I abuse all kinds of media, and I was eventually noted for this activity last year and got even an award for my bugs marketing and other writings. Before doing MySQL support, I was a trainer and a consultant working mostly with Oracle databases, and from that time I've got a habit of creating a clear, simple, useful presentations full of external links. So whenever in any of my presentation you see underlined text, it's clickable and it will bring you some new document that may be way more useful than presentation itself. Even though I work on MariaDB Corporation, in all my public writings and presentation, I speak only for myself. So a standard disclaimer of a kind is presented. My views may not be shared and may not be in line with recent corporation policies, so they are only mine. Do not take it as a direct recommendation or best practices for MariaDB Corporation or interpretation that they would necessarily share. It may not be the case. So speaking about tracing and profiling, there are different ways to do tracing and profiling for MariaDB specifically, and it all depends on two things: how much code changes you are ready to do, how much you want to be involved in the code itself, and the performance impact of the tools that you use. So to name just a few possible ways to trace, I'll start with the fact that you can basically use debug binaries. In debug binaries, in the large part of the code, each start of the function and end of the function is instrumented with debug macros that allows you to trace the enter to the function and the return from the function. And there are also debug printouts and key points inside some functions as well. With debug binaries, these debug outputs can be dynamically switched on and off at runtime with specific debug commands. The problem with this approach that was widely used at the early years of MySQL development, that was quite useful, is that you have to add this code into your source code of MySQL, and debug binaries are really slow, and when they produce a lot of debug outputs, they're even more slow, so it's not practical. A thing that works for seconds may start working for days, so it's not dynamic enough. Other tracing facilities are actually embedded in MariaDB and include extended slow query log, for example, There you can trace all the queries starting from those executed for 0 seconds. And for each query, you can write down how many specific row-level operations were used, or had it tried to use temporary tables, what had it tried to sort something, and everything. That's quite useful and show query execution profile in a lot of details. But again, it's written to disk, and enabling extended slow query logs for all queries will give you a huge performance impact, while still missing some details about the internal working of the server. More tracing outputs are available in MySQL and MariaDB, including show engine in DB status, show engine in DB mutex, if it's not yet deprecated. If we speak about InnoDB internal, some of them are presented inside the information schema with InnoDB tables there. For example, you can get some details about each buffer in the buffer pool, what page is there, how many pages are used, and everything. Again, requesting this information would give a notable performance impact, and it's just one of the details. A kind of a good balancing between details and impact was found by, I don't remember, probably Google initially, who created the user stat, later used by Percona and available in MariaDB as well. So at user stat, we have a key statistics on number of operations executed by specific user, by specific client connection, on specific table, or even index. It's a very popular profiling tool that can easily help to find out, for example, indexes that are never used for days and months, it's redundant. Or the most hot tables, speaking about the I/O. One, well, actually the first community contributed feature to MySQL back in 2005, as far as I remember, was implemented by famous Jeremy Cole, and it was profiled for queries. So the query execution was split into stages, and each stage was the time for each stage was separately recorded as a profile, and then you can show these profiles. It's still available. Show profiles allow a lot of details to be exposed about the specific query execution, why it's slow, at what stage most time is spent. Is it I/O, for example, opening table, accessing query cache, whatever. But it's also dynamic, so you can enable and disable it. It again does not provide enough details about other parts of internal server work. Performance schema that appeared in MySQL 5.5 was aimed to resolve this problem of show profiles and to provide an insight to all parts of the code that developers considered important to be shared. By instrumenting them, and that instrumentation was quite efficient. So the performance counters, time, and everything was recorded into ring buffers in memory, and re-recorded when the buffer is full. So it's quite efficient. And it's still used. Moreover, recent MariaDB versions, including 10.5, added a lot of additional instrumentation, including memory and everything, and it's more or less now at the same level as MySQL 5.7. So, beside that, it's normal when you use some operating system, MariaDB there is not the only software that requires profiling and tracing, so there should be some tools created by the operating system developers to work on their own kernel code to begin with. So there should be some way to trace the kernel, and there should be some ways to profile the execution. So you can see a lot of tracing and profiling tools provided at the OS level. It can be real profilers like Perf in case of Linux, or profiling tools on Windows, or it can be profiling like additional tools for profiling memory usage, for example, or for finding memory leaks, or it can be ad hoc profiling tools based on just periodic taking of stack traces like famous PTPMP. The last but not the least, you can get a lot of insights of how MySQL MariaDB works by just capturing the traffic. via utilities like TCP dump traffic on the wire. So this way you can capture the query and reply to the query, and you can see how much time is spent in between. And each network packet has a timestamp, so it's quite detailed, and it has zero impact on the server itself. So it's like a list of possible solutions. Of them all, I highlighted one that is specifically a topic for this talk. It's using OS level tracing and profiling tools. That's it. As we speak about Linux, there are 4 basic tools that I'm going to mention and speak about. First of all, the real trace interface appeared in kernel 2.6 about 11 years ago, and it's ftrace, function tracer. The ftrace appeared in a very easy way. The reason was that they had to resolve the problem in kernel, and it was an extension based on the idea of GNU profile. So when the program was built with profiling information, a special code was inserted at the beginning and at the end of the function, the same way as I've explained in case of debug package of MySQL. And at these moments, data collection happened. So they extended this existing way to compile the code and added a way to dynamically replace part of the already pre-existing code with calls elsewhere. So, and then expose the resulting information via the files interface. That's ftrace. Then on top of ftrace, really soon, real profiler, as I called it, the best Linux profiler with the least impact, the most dynamic one, called perf, was added. And this was already a convenient way to add my favorite way of instrumenting the code for tracing and profiling, so-called dynamic probes. So it's possible for more than 10 years already for any binary running on Linux, including Linux kernel itself. We should use it for databases as well. On top of that, on recent kernels, starting from 4.9 specifically, was already quite complete, and specifically with Linux kernel 5 and more recent ones, even better tracing tools with less impact, more efficient ones were added in the form of eBPF, or extended packet filter. BBBBB stands for Berkeley, surely. Actually, in frames of BSD, they re-implemented tools like TCP dump and packet filters in a way that to make them applicable not only to network events. And they did it later in Linux, re-implemented it again on top of a virtual machine that safely can run in kernel context and most efficiently collect the metrics in memory buffers, like in performance schema. So on top of eBPF, raw eBPF required programming and using the related API in languages like Python, for example, or Lua. Then on top of that, command line tools, so-called BCC tools, BPF compiler collection. So as soon as API were implemented, these tools were already written, and you can use existing tools, write your own. That's what a separate team in Facebook does, for example, where they use eBPF a lot. And finally, the last edition that is usable in kernels 5 point something, like on Red Hat 8 or recent Fedora and such, and recent, like few years old Linuxes, is BPF Trace. BPF Trace implemented a safe and quite interesting language in Aveka style that produces the program for that in-kernel virtual machines without the need to code in Python and use API directly. So you just script it, extended scripting language. So this is I am going to speak about these tools. Why not performance schema? There are 2 reasons. One of them is historical, and well, there are more, and I will present them. But most importantly, it's all about the performance impact. And another historical reason is being able to add probes dynamically. If you have to change the source code to instrument something, if instrument is missing, like it happened with performance schema, it's a serious deficiency for my work. I am not a developer. I am a DBA and support engineer. So I need a solution right now and here with existing code. I cannot wait for the instrument to be added. I need it to add it dynamically. That's it. So yet another reason why I do not discuss performance schema here is because it's discussed elsewhere. During this event, MariaDB Server Fest, I have another presentation explaining mostly the details of additions to performance schema in MariaDB 10.5. One may argue that performance schema is inefficient in a sense that it adds a lot of additional memory in server. That's true, and it's even more true in case of MariaDB. It changed a bit to better in 10.5, but in general, yes, you need to keep that memory buffers for every instrumentation point. It doesn't matter if it's used or not, until recently. In 10.5 and in MySQL 5.7 later, we have dynamic allocations for memory for some instruments, so it's not that bad, but it's still not dynamic enough. One another thing is performance schema may not be even enabled or compiled in. It's not enabled by default in MariaDB. It's not compiled in some forks like MySQL at Facebook. And even if it's compiled in, it still may be not enough dynamic because some instruments up to this day can be enabled only at server startup. So if you were not there and had not an idea that you need this instrument enabled, it may be too late. You cannot check memory usage of the InnoDB buffer pool unless you asked to instrument memory at startup. That's it. Sizing buffers may be a problem, so that finding that trade-off in between size of the memory additionally allocated for performance schema versus the number of details and frequency of changes that you want to capture is a real problem. So with performance schema, you may spend a lot of time trying to size each instrument properly to get the smallest performance impact and still not missing the detail. Another thing that I hit that we cannot expect, while Oracle would like us all to add performance schema instrumentation everywhere, they cannot force it, and we in MariaDB cannot force it. So, for example, inside Galera library that is quite popular among MariaDB users, the amount of instrumentation in performance schema is quite small. And we can do nothing about it because it's third-party plugin. There are third-party storage engines, so we, again, cannot be sure how much they instrument. We cannot influence that. Yet another thing is, usually when you are troubleshooting, solving some problems, you approach them from two sides, from your software, from MariaDB server side, internally, and from the operating system side. You need to monitor operating system resources. If you use different tools to monitor and trace for your software versus operating system, you have to somehow summarize and put them all onto one plate and use together. So first of all, you pay the price twice for tracing at operating system level and for tracing at your software level, and then the results may not be compatible. So that's it. The last but not the least is the following. In MariaDB, we in support work actively and closely with developers. So when we report bugs or issues, we need to provide the information the developers asked us to provide. So they do ask us to provide stack traces whenever there is some hang or some slowdown or any performance problem. And performance schema doesn't give you stack traces. It may give you a set of stages, statements, transactions, everything, some insights following some functions in the code, but it's not a complete stack trace. So that's what we requested. We got requests for stack traces, so we need tools that produce stack traces. It's not performance schema. And for me personally, performance schema requires too complex SQL queries for many tasks, and as I often do not have them collected and prepared, if I need to invent it on the fly, it's too complicated and takes too much time. So what do I suggest instead? I suggest to use modern Linux tracing tools. if we get to this picture of all the utilities that you can use to get performance information from, there are many, and most of them are probably known for you, from top to PS to free, SR, and whatever. I am interested in this specific part: ftrace, perf, BCC tools based on eBPF, and BPF trace specifically. As you can see from this line on the picture that I borrowed from Brendan Gregg, they cover the entire stack, from the I/O to kernel details to applications, and with libraries, APIs in between. So you can trace everything with the same tool. That's the point. This approach is quite popular for maybe the last 5-6 years, and there are many famous people who are writing about it, so just follow the links. Now, what are we going to trace, and how do we approach the profiling? There are 4 types of event sources, so we will try to capture events. So there are 4 types of event sources that we might be interested in. They can be presented in such a simple table. So first of all, there are some events in the kernel. For example, if we are tracing and dealing with I/O problems, I/O is implemented by the kernel, so at some level. So we may be interested in what's happening at the kernel level. And there are event sources in applications or in user space, as I put it here. Now, from another dimension, it depends on pre-existing instrumentation that was in the source code of the kernel. Then it will be a kernel trace point, or in the source code of the application software. It's like what happens with performance schema probes, just they are not accessed by these tools. These are so-called user-defined statical tracing, userland statically defined tracing as well, simply dtrace probes. Based on dtrace in Solaris, that was the first dynamic tracing tools widely used, and like a father of all dynamic tracing. We do not use Solaris anymore these days, and dtrace, while it's present in Oracle Linux, theoretically is not easily available outside. So kernel developers of Linux had to invent other options. So manual annotations mean that you have to change the source code, then recompile, and then you add event source. It's inconvenient and it's not dynamic. So another way is to add dynamic or automatic probes, and this is what we are interested in. So you can do it in kernel context, and it will be a kernel probe. Basically, you can add probe to any kernel source or function. Or you can do it at user level. That's my point of interest for this talk, so-called user probe. So you can add tracing events dynamically to functions without changing the source code. That's the greatest way to do things. So, okay, you have event sources. Let's assume you somehow defined some events for your software, for MariaDB. How you can access the event sources based on the tracing framework that covers the entire system that I am going to discuss here. It's Linux, so it's Unix. Everything should be available through some files. So yes, you get access to event sources via the files in a special kind of file system, TraceFS, that can be mounted on SYS or elsewhere. Here, let me finally go to the terminal, and here is what I'm speaking about. So we have TraceFS mounted here at syskernel tracing. So then we can just check syskernel tracing, what is there. Now the first problem that I'm going to mention with this tracing approach is that you need sudo or root access. So unfortunately, for developers who do not own the server they work with, it may be a bit complicated. But yes, that's what we have there, a lot of subdirectories, files, whatever, and they will be dynamically added and removed depending on what tracing facilities you do. So how do you deal with files on Linux? You read files and you write to files. So that's the basic way to deal with event sources. You can do it from command line, you can do it from the system calls, that's it. As a result of your writes to some files in this TraceFS file system, the source code of the functions is modified on the fly to add tracing events. When you are done with it, you stop tracing, that instrumentation is dynamically removed. So you pay the performance price only while you are tracing. So you can add trace points dynamically and remove it when they are not needed. You can add them on the fly only for the period that you need. And you do not use neither CPU nor memory when you are not tracing stuff. So these files, numerous files, are not so easy to deal with, easy theoretically, but a lot of commands to type in practice or a lot of code to write. So we need some front ends. With time, when this dynamic tracing system evolved, on Linux kernel, several front ends were added. The first was perf, then BCC tools were added, then the latest one is BPF trace. They're all front ends. Front ends are truly optional. So as soon as we have the file system mounted, that's how it's mounted if you don't have it. We see some file there, we have seen that. We can check what is there as we were interested in dynamic user level probes. So let's check uprobe events. Tracing uprobe. Yes, so what is it? We can get access. It's a simple file. It's empty now, so there are no user probes. The file exists, but it's empty. Okay, so to add the probe, we had to write something there. Then it will not be empty. If you do not want to write something there manually, you can use tools based on top of these files, command line driven, that already simplifies this process for you. Let's skip it, and we can still do it manually. Let's assume that I would like to add a trace point, a probe, to the dispatch command function in the MariaDB 10.5. So the first problem that appears if I use ftrace directly is that I need to find out the address of that function relative to the binary. So because for the probe, I have to provide the address. Ftrace does not know anything about the source code, it just needs to know the address and try to do something with it. So how to find the address? To find the address, you can use the objdump. There are different ways, it's just one of them. With T option, provide the binary and then search for the command. Here is the address, you can see. The function name is mangled because, well, that's the way it works. We may have to use mangled names later with other front ends. So with ftrace, we need just address. So we can add a probe, P. We can give it optional name. If we do not give a name, then the name will be inferred from the binary name and function name, or whatever. So we give explicit name, DC. The binary is listed here. The address is listed here. Then for dispatch command, we would like to print the query, which is the argument. The argument number 3 for dispatch command. Here, it would be interesting probably to find out how do we know. We need to know the source code. We can study it, or we can use it and study with GDB. So we can attach GDB of MariaDB. I already used branded names for 10.5. It's MariaDBD. So if we attach to the binary, we can add a breakpoint, for example, dispatch command. So then if we try to, for example, connect to MariaDB, surely we have to continue here. Okay, so that's it. We started and we already executed some command. So our breakpoint fired, and here we have a query. We can see it as a third argument called packet. So here we can just print the third argument and see the query. It's asking for the version. So if we queue it from here, that's the knowledge we need to add dynamic event as well, user probe. So we detach from GDB, get back here. So that's what we do. We need it's a third argument. We should know how arguments are passed for our platforms for ftrace. Its third argument is passed by the register in the register that should be accessed as DX, so not extended. Just DX, trust me. And I am printing the content of the register. +0 is also important to get the address right, 0 terminated, as a string, and we give it a name of query. So if we write this text to the uprobe events, we can append it. Now we just overwrite, but if there are many probes, we have to append. And then enable the specific probe, and then enable tracing. We can then read the content of the file, some file. There are several, depending on what you trace and how you trace. For example, trace pipe and get the resulting query. So the idea of this test was to capture the queries on the fly. You can do it for 11 years already. There are details presented in my separate blog post. So you can access event sources and add dynamic probes with nothing but ftrace. You do not need perf installed. You do not even need GDB. All you need is objdump to find the address and knowledge of the source code. That's cool enough. So what are the problems? The first problem is already known. You need root access. How to get address? Well, objdump helps. It may get complicated, unfortunately, with C++ and other modern software, with Java, for example. I am trying to show some of the problems and solutions in a separate blog post. How to work with function arguments? Okay, if it's just a simple argument that can be used as is, as in our case, we just need to know how it's passed. But what if it's a structure? So eventually we can access any memory area. It's not going to be safe, but we can try. And well, probably we can figure out how to print structure as detailed as thread, for example, in case of MySQL or MariaDB. But it's complicated. So this tool works easily only for simple functions, ideally written in C. Then what if we would like to add a trace point at the end of the function? For example, let's consider allocating memory. If we want to trace memory allocation, we probably need to know the size of the allocation and the address that malloc function gave you back. So with this address, you can then store it somewhere and then trace also the free, and then you can see if something remains after some time of working, how much memory is allocated in total and everything. So for the probe at return from the function, there is just another type of the probe. It's R, return probe, and you can access readval. The return value from the function. Again, you can print it differently. You should know the data type. There are only a few basic data types supported, so it's all getting complicated. When you are done with the probe, you can just clean up everything from your probe events, or you can just remove the probe by name with minus. In more or less complicated cases, I had to, and that's my suggestion, actually use a front end like perf to add a dynamic probe and then check with the TraceFS mounted how the probe looks like. That this way you can study how it's done. It's complicated, and I'm going to spend more time with months and years on how to do it with pure ftrace, because ftrace is always there. Some customers may not be able to install additional packages due to their internal security reasons, but they do have ftrace. So they may still have problems with root access, but that's another story. Then with no root, all this is not for them. So the oldest front end is perf, which is actually a sample-based profiler. But we will use it for adding dynamic probes as well. Perf basically, it has dozens of commands, allows to record the profile, to create a report based on recorded profile, to show the recorded profile data. Perf top is kind of top, but with top functions. It's interactive utility showing what spends most of the time based on your sampling. And actually the way to add a dynamic probe with perf is perf probe. What a surprise. So with perf probe, you can add similar probe to the one we already discussed previously with a much more user-friendly command, just dispatch command. Is a function we want to trace, and we want to print packet. We already seen it's a variable. It's variable name as a string. No mangled names, no addresses. That's it. Then we can start recording. It's sampling profiler. We can set up the frequency of recording so we do not miss any calls, or without frequency it will be picked up automatically. So we can do recording for some time, for example, until we stop it. And then we process the result with perf script, and then with this probe added, we can see the queries captured. That would be the output from MariaDB. When we are done with the probe, we can delete it by the name. So that's easy. The name of the probe will be shown to you when you create the probe. So you will see that the name is like probe dash binary name, short MariaDB D, and then a colon and actually a function name. The rest are optional parameters. So yes, we can see the queries this way. Moreover, we can also see the binary, process ID, CPU or core on which it runs. There is a time starting from the start of recording, so we can see how much time was spent on our probe. Then the probe name and probe arguments. There is also the address. So you can do a lot of things to control this output format. As it's visible from that simple example, it's way more user-friendly than ftrace, because you can use names, you can access, in many cases, you can access complex structures, records inside records with pointers and everything, not always, but often. And still, while it's more easy, you may have to study source code and do some checks in GDB to find out what exactly you would like to print. Problems. Are there any problems? Usually no, but for example, when I try to use this approach for MariaDB 10.3.18, as far as I remember, on my old Fedora box provided by Fedora, it was Fedora package, at that time, that same function dispatch command was implemented differently. It had a comData structure argument where the query was in comQuery point query. And when I tried to add the probe, it had not worked. I was not able to dereference this the argument properly. I had not spent enough time, and I decided on that and decided to go an easier way. There is another command in the stack for looking for the queries. It's do command, and at that version it had also the packet, and packet contained the SQL statement. So I tried to add it, and I failed. So whenever you cannot add the probe for whatever reason, you see it. So the packet was a local variable at that moment, and I was not able to access it. at this stage. I could access thread parameter, but it was too complicated, and I was not able to figure out how to do it. So what I did, first of all, I was able to check that theoretically in perf you can access all the variables. So yes, I was able to access the thread variable. That was the only argument for do command at that time, but I was not able to go farther. Next thing, that packet was a local variable that was available, and later, this is how it was declared, and it was initialized later. So there was a way, and there is a way, to add a dynamic probe. As you can remember from ftrace, it's added to the address. That address is not necessarily the beginning of the function. Actually, any executable command can be replaced by the interruption code int3, and then the probe can be added dynamically on the fly. So to find out which lines of the code can be instrumented, there is a line, not lines, or it's a typo line command. So for the specific function, you can show a line that you can attach to. And of all the lines, I found out that line 157 is the one where the local variable packet is already declared. And it should get the proper value. So I tried to add the probe there. The syntax is quite simple. You add the probe to a specific line of the function. You can add the probe actually to a specific line in the source code file with another syntax, but similar. And I print a variable named packet as a string. And I've written down everything, started recording, and got my queries again. So what's the lesson we get from this? All this exercise was a result of the fact that simple command had not worked. But I found out that with perf, you can easily, it's a convenient front end, you can easily add a probe, dynamic user probe, to almost every other line in the code. And access local variables there. So it's the most dynamic way to trace things you can imagine. You can add the probe after every other line in the code, before it and after it, give names, and measure the time spent executing this specific line of the code. Not without, not with recompiling, not with adding performance schema instrumentation, not without waiting for anything, just on the fly, and it works. Besides user probe, you can surely use kernel trace point. For example, it's needed when you try to measure time spent on I/O, for example. You can do tracing not only for MariaDB server binary itself, but you can trace shared libraries as well, those that are dynamically loaded. This is how I trace malloc calls and size of allocations. This same approach was already applied by my colleagues in MariaDB to a software called MaxScale. You probably know about it. So it's not even a server. You can apply it to anything where a memory leak was suspected. So all the details are already shared in a blog post. In another blog post, I've tried to apply it to C++ and was successful. That was a case of MariaDB 10.3. In 10.5, I found out that this member function became virtual, and for virtual functions, you do not even you are not even able to add a breakpoint in GDB. So you cannot trace it, or at least there is no easy way to do it. So these practical examples show you that problems are real. Not all of them can be avoided. Just a few words about perf as a real profiler. That's the first use for it for myself. Perf is easy to install. Perf is easy to use. For profiler, you usually, as it's sampling profiler, you usually set up a frequency. How often, how many times per second you want to stop the execution and check your trace points or capture the stacks. That's how profiler works, and measure everything. There are default frequency. It can be self-tuned by the perf itself. 99 samples per second is usually enough. Then you can record forever. The more you record, the more data are recorded. The data are sampled by reading from that tracing file system, and they are put into the user space. Writing files into the user space takes time and resources and disk I/O. So usually you do not profile for days, you profile for a short time. So you can profile just function calls, or you can also write down stacks. So with -G, you write down also stacks. You can profile specific CPU or all of them and many more things. So you record your profile. When you are done, you can, for example, stop recording the one way or the other. And you can get the profile. You can get it dynamically too. I will just show that for the, let me queue it from here. For some samples, I have a sysbench command running, and in another terminal at the same time, I can do like perf top. Yes, and you can see where most of the time is spent at the whole system level. It might take some time. The load is really high. The frequency is already decreased. So let it work for some time. As a result, if you are writing down stack traces, you will be able to get a tree of function calls with percentage for each. Oh, here it is. So we can see that, for example, most of the time is spent on Unix. A lot of time is spent in MariaDB. You can step inside, zoom into the thread. See, it's dynamically changing. So when you are done, you can queue it from it. Sorry. So I will not overload the machine while it's recording. So one of the basic examples from my blog post, probably 4 years old already, shows a case that turned me to dynamic tracing entirely. So the case was simple. At customer side in a complex Galera setup, simple queries like select single line by primary key often hang for 13 seconds, for example. And the idea was to find out why they are slow sometimes, sometimes not. There was a lot of concurrent activity and everything. I tried everything I could with performance schema, show profile, and whatever. And I found out that a lot of time is spent at statistics stage. So calculating statistics. What statistics? Why? It was not clear why it takes so much time until I've got a profile with stack traces. Here's where the most of the time was spent. So yes, it was in statistics. We were reading the data from the table. You know, in InnoDB, when you need to find a plan for the query, and you are looking for the key, you have to find out how many rows you may get for this key. So it was really a reading of data from the table. And why it's slow, why reading one line is slow? It was waiting for in the QE to enter the InnoDB. The problem was really that in that case InnoDB concurrency was limited. So when there were other, for example, 12 queries for 12 cores or doing something for quite a long time, like doing big updates to unrelated tables, such a simple statistics request was blocked. So the resolution was simple, remove the limit, but I studied quite a lot on that. Among things that I studied was that performance schema is not detailed enough. Performance schema does not document stages of statistics calculations and many more things. But really, dynamic tracing and using perf profiler was a solution to a real practical problem after everything else had not worked. And the detail was missed surely by me, and everything depends on the load. Under some load, everything works, then it does not work. So we tried to capture the statistics for and the information for quite a lot of time. In practical cases, the call stacks and such graphs, they may become huge and not easy to work with. The samples collected themselves can be huge. So when I was collected I/O requests at kernel trace point for 60 seconds, it took 33 megabytes. Writing 33 megabytes on some hardware may be already time consuming. So, to summarize, what are the main problems and challenges if you have root access and you mastered the tool? There are two. First of all, perf at the front end that writes everything to the user space is having too large impact. What is the solution to these problems? Use a lightweight tools. So if it would be possible to process the data, not after the fact, after the collection, but on the fly, that would help a lot. If that would be possible in the kernel context, without touching the user and passing to the user only the result that is needed, that would be perfect. And eBPF gives us that. And another question, what to do with such a complex profiling information when it does not fit on many pages on screen? So you have to summarize it somehow. The answer to this is post-processing tools. Of them, the most popular right now are flame graphs and other heat maps. So you have to summarize and visualize this data in a way that are easy to use. That's a bit beyond the topics of this talk, but you will see how it looks like. So, as a way to reduce the impact and trace safely and summarize safely whatever you need, eventually eBPF was developed. When porting dtrace proved a hard task and stalled. eBPF is based on Beckley packet filter that is behind TCP dump. The idea was that filtering should be executed at kernel context, so efficient, but it should be safe, so it should be in some virtual machine. So they had rewritten the code to run in a virtual machines that was efficient because the code for it was JIT compiled, just in time compiled to the machine code. So there was an extra level of safety, there is an extra level of verification before the code is allowed to run in eBPF virtual machine, and for this eBPF to be useful not only in network stack tracing, it was provided access to kernel probes, user probes, static trace point in application sources, performance events, and almost everything. Same as performance schema, eBPF writes down to the memory areas in kernel. And then these memory areas can be read by end user. So it's as efficient as performance schema. Maps are limited in size, so memory is also not abused. And you have access to all the internals in the kernel. And you can summarize things in the kernel. So more or less up to the kernel 4.9, all this machinery was implemented, tested, and widely used. So the problem was with front ends, how you write the code. You can write LLVM, it's LLVM virtual machine actually. You can write assembler code for LLVM, but it's too complicated. So there were APIs ported to Lua and Python, and at this moment people started to create a lot of tools in Python doing all kinds of things. For example, access to dtrace, static trace point that some software still had supported. So it's like people decided to stay dtrace compatible when they implemented different previous tracing frameworks for Linux. So we can, for example, do that same thing as we did printing queries on the fly using the static trace point if it's defined. So that's how it works. I should say that MariaDB binaries do not provide dtrace, and MySQL 8.0 just removed dtrace probes entirely. Fedora conveniently had them compiled, so I was able to capture the queries this way without anything else, just by using a ready-to-use BCC tools and already existing in the code static trace points. So the same way with trace, you can add with similar tool called trace, you can add dynamic trace points. You will still have to use mangled names. You need to know how arguments are passed. You can see it in my blog post how it works. So you can write your own BCC tools code in Python if you're a developer, and entire teams, as I said, in Facebook, for example, That's their main job, to write such a code. If you're a DBA or a support engineer like me, not a developer for decades, if you do not have Python installed, you may still write down quite efficient custom tools to summarize the information provided by the kernel using the newest front-end called BPF_trace. So it does not work, for example, on the machine I am currently working on Ubuntu 16, but it's really old. Whenever you have kernel 5, you already should have a working BPF_trace. There were some problems on Fedora 29. Starting from Fedora 31, they are mostly resolved. That's based on my experience and what I was told. How BPF_trace works? You can actually study the tutorials, but basically you provide the program. It's like AWK. So the program looks like you have a pattern. If something matches the pattern, there is an action. So it's a set of pairs pattern action. So if you see something, you do this. As an action, you do not have loops, unlike in AWK. So there is a guarantee that BPF_trace program always complete. It cannot hang, cannot loop, cannot hang the kernel virtual machine. So you add the trace. You basically add the trace point. For example, syscall, sysenter for all of these. For a specific syscall, like here. So it's a pattern. So whenever we see this call, we do print the arguments. So these are open files, for example. So basically, that's it. You define several probes. Then you can match additionally the probe against some filter, and then there is action in curly braces. So how it may look like in practice? Besides trace point, BPF_trace is also able to act as a profiler. There is a special probe called profile. You can set up frequency, same as with perf. You can add a filter. For example, you do not profile the entire system as we did with perf_top. You profile only MySQL_D, for example, or MariaDB_D. And then what you can do, you can print user stack, in a perf compatible format. There are two kinds of formats, and you collect stacks same as we do with perf profile. Here is the content. So we do calls, dispatch command, do command, everything. Thread pool was active, so we have a callback here. So you can check my blog post for details how to use this in practice to have both user space trace and kernel space trace sampled 99 times per second. This is how it works. Why should we care? Why should we bother? Because of the performance impact. So with eBPF, no matter how you access that, maybe by BPF_trace, you have the smallest performance impact. I was running similar sysbench test on another system, and I've checked the queries per second executed with different dynamic tracing options. PTPMP, poor man's profiler. So we got a drop to just 56% when we collected once per second and missed many samples. If we try to collect more often, just all hands. With perf record, we had 98% of queries per second, so there is some performance impact, mostly related to writing down this amount of data. And with BPF_trace dynamic profiling probe, when I've counted, similar to what we did above, I've counted the number of unique stack traces. So I've got just 0.13% of negative performance impact with 99 samples per second. With higher frequency, it will be much worse. Few words in conclusion on how to represent the data. You can read a lot about the flame graphs. All these tools, dynamic tracing tools, their output formats are taken into account in this set of tools developed by Brendan Gregg, so you can process stack traces from PTPMP, from perf, or you can pre-process whatever stack traces you see. You can use BPF_trace directly. You can use pre-existing, pre-built Python-based BCC tools. For example, if we try to find out where the time is spent if it's not on CPU, we can use the existing off-CPU time utility, produce text, then collapse them and present them graphically. We see where most of the time is spent here. Let me summarize the problem of dynamic traces as we are going out of time. So, first of all, you need root or pseudo access. In some cases, you need literally root access. As I see from my experience, and as we could see maybe from samples I will share during the chat with you, there is a problem to debug the problem of the program when it is traced. So GDB sees a different code than it expects. It does not really work. So it's still a problem to find out the amount of additional probes and the trade-off in between the details you collect and the amount of memory and CPU you spend on collecting. Adding dynamic probes to C++ and complex code of that kind or to Java may be problematic. Using BPF trace to access source code may be more problematic than perf because you have to pass headers. It needs to know structure. Surely for all of this to work, you have to build with a no omit frame pointer. If we cannot get the frames, we cannot get the information. In case of pre-built packages, we may need debugging for packages so that symbolic information is available. In some cases, we have more tools to install, but with ftrace, it's always there. The most important with all tools above and beyond perf is a lack of current practical experience. It's my own problem as well. I had not used them often enough to really be fluent with them. But I'm still not the only one who is suggesting this stuff. People do dynamic tracing even for Oracle RDBMS, and you can find out a lot of other additional sources of information about this. So that's all from me. As usual, if you ever see a bug or a problem in MariaDB, report it. Thank you very much.